Is the mic on? Can you hear me? Yeah? Good. Okay. Okay, so we're going to not talk about Lab 11 until Friday because I want to talk about Homework 3 today. We're going to take the hour to talk about the homework assignment. If you have Exam 3 regrade requests, you do them through Gradescope until Friday when it closes. We're still grading Homework 2. Now that the exam's graded, we can turn our full attention to doing that. We should have it done, I hope, quickly. And Homework 3 has been released. How many have started or at least downloaded the homework? So there's a lot to go over because there's material there that we haven't covered. And normally what I would be doing now in this class is I would be parsing and working with War and Peace, the novel. But we're not going to do that because it's very similar to the homework assignment. So I want to spend time on the homework assignment instead. But as you read through the homework assignment, you probably recognize some of the things that we've been doing in class. In particular, there's a list of regular expression substitutions in the homework at the beginning of the template file that should look familiar to you. It was the motivation for studying regular expressions at all. You remember in our original attempt to parse text from a novel, we had a list of 82 contractions that we had to substitute one after the other, and that was reduced to something like 8 regular expressions, which are in the template file. So that's where those come from. So this homework follows directly from what we were doing in class. So we use the same kind of concepts we've been using, very light use of regular expressions, somewhat more just basically text manipulation concepts. And the problem we're trying to address here is I'm giving you a corpus of text, and I want you to do some essentially authorship identification. So you've all encountered Turnitin, right, when you turn in term papers and things. And you might have wondered how that actually works. Well, this lets you see a little bit behind the curtain. These are very rudimentary techniques. There's many better techniques, things that are more sophisticated than what we're doing. But this actually works reasonably well considering how simple it is to do. So we're going to work with the corpus of speeches that come from the Miller Center Repository at the University of Virginia. This is a center that studies the presidency, and they have a collection of speeches given by all the presidents. So I downloaded a bunch of these speeches. I tried to get them all approximately the same length. They used to let me download them with a single command, with a wget command. Now they're harder to download. So the last few presidents, I didn't quite pick the best speeches. I just picked ones I could get to easily. But there's 164 speeches from 41 presidents in the corpus. I don't have anything from Joe Biden yet. For some reason, I don't have anything by William Harrison. I have Benjamin Harrison, but not William Harrison. I don't know why. If you know the president numbering system, there is a little quirk that took me 10 minutes to remember, is that there is a president that was elected twice with somebody else in between, and so he actually has 2 presidential numbers, which is why this didn't multiply out. That's a silly thing, but anyway, so I have 4 speeches from 41 presidents, 164 speeches of varying lengths, and I have 5 unknown speeches that I want to identify using this document similarity idea. You will recognize the speeches. If you look at them, it's like the Gettysburg Address and the Day of Infamy speech. These are speeches that you studied in high school probably, so you know who the authors are. Okay, so normally if I were doing this for real, I would go to the Python documentation site, and I would find out that there's this really nifty toolkit called the Natural Language Toolkit that provides a lot of the primitives that you need to do this kind of document manipulation. So if you're interested in building, say, word frequency vectors that we've done by hand, right? Or if you're interested in stemming words to find words that have the same root and collapse them to a single, root stem, there are tools for doing that in Natural Language Toolkit. So we're not going to do that though, because the point here is we sort of want to understand how the techniques work, and I'm not interested in doing a really good job with this. I'm interested in doing a passable job while you learn to code this stuff. So we're just going to build our own stuff. However, if you have time off in the summer and you want to have some fun, I'd encourage you to download the Natural Language Toolkit and try doing this project for real. I think you'll find that you'll do much better than what we do in the homework. Okay, questions so far? Is everybody with me? All right, so what's the regular idea here? Well, I've got this corpus of speeches. I'm going to read in each one of them. Just read in the text. I'm going to do a little bit of text manipulation to sort of simplify the text, to regularize it. I'm going to strip punctuation out of there. I'm going to separate it into sentences. I'm going to replace question marks and exclamation points as sentence enders with just periods. I'm going to try to make it simpler. I'm not going to remove case yet. I'm not going to worry about identifying proper nouns, which is also a thing we could do. I'm just going to make the text a little bit simpler and leave it alone otherwise. I'm going to build a vector space representation of the text, which is the topic for today. What is a vector space and how does that work for text identification? And then, oops, there's a T missing. I'm going to find the closest vector space match for each of the unknowns. Okay, so what I want to do, well, let's talk about these one at a time. So this is organized in a very object-oriented fashion. So we're going to have two classes. The classes are in the template file. One class is called corpus. It represents the collection of speeches and associated methods. The other class is called speech, and it represents an individual speech, the text of an individual speech, and has appropriate methods. Now, originally, and I apologize that I didn't get this assignment out as early as I thought I would. I thought I'd have it out Monday. But when I first wrote the assignment, I thought it was too long, and there would be too much to do. So I wanted to reduce it in a way. But then I found that as soon as I did one part of it, then the other parts were sort of trivial. So I had to come up with an inventive way to just give you part of it to do. So I've given you most of the file. There are 9 little parts that you have to write, and they're all identified with Fix Me in the template file. Some of these are very straightforward, very short little excerpts. But you have to understand the entirety of the code to get this to work. I don't think this problem will take a lot of time coding. I do think it will take a lot of time understanding and testing and making sure that you understand how to compute the things you're told to compute and making sure that you compute them correctly. And each one of the 3 stages has its own set of little quirks. So you're going to have to start by reading the entire template and making sure you understand what it does and how it works, and that's part of the reason we're doing this today and spending a day on the homework. So there are 3 things to download. There's a short PDF file with a write-up that explains vector spaces, term frequency, and inverse document frequency metrics. Very briefly, you can always go to Wikipedia if you want to know more. There's a zip file called corpus.zip that contains all of the speeches. And then there's a template file which you should use for your assignment. Questions? Okay, so you unpack the zip file into an appropriate subdirectory or subfolder. Now I've done that on this machine here just now. I just downloaded the zip file and unpacked it on the desktop in a folder called Corpus. You need to know where these files are located. In the template file, it assumes that your code lives somewhere, maybe on your desktop or maybe in a folder called CS1210, wherever it lives, that there's a subdirectory or a folder in that same directory called Corpus that contains all the speeches. Now you can change that. It's a parameter in the template file, and you can give a direct address. I mean, you can give a full path to where Corpus lives. I don't care how you do it, but you need to know where the text files are in the code so things will work out for you. Now the template file contains corpus and speech. So let me just pull this template file over and we'll take a look at it. So far this should look pretty familiar. It looks like any other homework file. We have a few variables I'm about to talk to in the next slide. And then we have the definition of the corpus class with all its associated methods And you can see the fix me methods here. And we have the class, speech class with its comments. And you can see the fix me comments in line there with what you have to fix. Now, I tried to avoid giving you the regular expressions to derive because I think that's hard and you've had a taste of it. If you did yesterday's lab with regular expressions, then you have a taste of how hard it can be to write a good regular expression. I don't really want to have you waste your time with that. I do want you to work a little bit with regular expressions, so you should at least understand these. And we'll talk about this in a few slides. If you go to the very bottom of this, you'll find, let's see if I can bring this up. Oops. The very bottom of this, you'll find this little passage which can be loaded at startup. And you'll notice what this does. It creates a corpus object which to represent our files. And then for every president, for every number from 0 to 3, these are the texts of speeches. Every speech is labeled with the president's name. So it'd be like Obama 0, Obama 1, Obama 2. So we construct the speech names, and we're going to call corpus add speech with the name of the file. This will find the file in wherever your corpus directory is. It will create a speech object, parse the text, add the speech object to the corpus. And so this is all preparatory work. It sort of gets, it builds your corpus representation and the vector space representation. And then for every unknown file, this is the list of the unknown files, we'll print out our little mystery speech identification. So that's how that works. Let me show you, oops, I don't want to do that, but okay. So this is I'm going to run this file. Just so you know, it's not particularly fast, right? Because you have to, first you have to click on the right button. So you have to load in all those 164 speeches and process them. Did this take the click here or not? Yeah, it did. And then you do the identifications. And let's see what the output of the template of the homework is at the end of the day. So if you remember the little template at the end of the template file, there were 3 parameters to identifying the unknown. First one was which unknown were you identifying. So we had, mystery speech 0, 1, 2, we had 5 unknowns called unknown 0, unknown 1, up to unknown 4. And then there were 2 other parameters. One was a parameter k, which said how long the vector space, how many dimensions in my vector space, which we'll describe shortly. And I'd set that to 1500. So there's 1500 dimensions that we're matching in. And then the second thing was the second parameter, j, which I set to 4, which basically says, give me the top 4 matches to this speech. Okay, so for mystery speech 0, the top match was Hoover's third speech. The next top match was Coolidge's 0th speech, then Coolidge second, and Benjamin Harris's second speech. So these are the speeches that are from our corpus that were found to be most similar to the mystery speech 0. Okay? And for each one of these speeches, mystery speech 1, Roosevelt, this is Franklin Roosevelt, was the closest. Nixon was the closest for mystery speech 2. Mystery speech 3 was Roosevelt, and so on. And all of these, you can see that they're associated with a number, which is sort of the quality of match. And that number is a number between 0 and 1. It's a floating point number between 0 and 1. The higher the number, the better the match. If I were to attempt to classify a speech, an unknown speech, that is also in the corpus, I would have a 1. Okay, meaning it's a dead ringer, it's a match. If it has nothing in common with the speech, any of the speeches in the corpus, or sorry, if you compare an unknown with with a speech in the corpus and they have nothing in common, it'll be a 0. So we need to get to, by the end of the day, understanding where that number comes from. All right? Or questions? Are people okay with this so far? How many of you started the assignment? Is it helpful to go through this, or yeah? Okay. All right. So this is what we're after here. And by the way, the classification is not that good. right? This gets 3 of them, maybe 2. 3 of them if we consider top 4 matches, right? So for example, our last speech is actually Wilson, and it's number 2 here. It is a Hoover speech. So, but Hoover was notoriously long-winded, right? So there's a lot of text to match. So some of these are really kind of sad. I mean, the Gettysburg Address, which I think is number 2, gets attributed to Nixon. You know, there's some irony here. But remember, when we're using this kind of representation, let me just say something in defense of the approach. We're not really saying that the speech is indicative of the author so much, because most of the presidents don't write their own speeches. They're speechwriters for that. Sometimes multiple speechwriters. It is the case that presidents have their own sense of vocabulary, right? They use typical, maybe political catchphrases get used many times in the speeches. Depends a little bit what the speeches are. I've got everything in here from State of the Union speeches, which is Hoover's speech, to things like the Gettysburg Address, which was a very short speech, right? Gettysburg Address is not that long. It's a couple hundred words. So we have a broad variety of types of text involved. And finally, I should say that similarity often is a consequence of the times. All right, so if you were president in the Great Depression, your speeches tend to focus on the economy and shortages and so on, and any speech at random I give to you from Hoover is likely going to be economic in nature. It's going to talk about production and so on. If you lived during the Vietnam War, if you were president, Nixon, Ford, Kennedy less so, Nixon, Ford, Carter, Reagan, Vietnam, the word Vietnam is going to be in your speeches. You're going to be talking about the war. Just like Obama and the others, Bush, talked about Iraq. So the times do sort of indicate what the speech is about. Even better example, I bet you the word pandemic appears a lot in Trump and Biden speeches. We don't have any Biden speeches yet. I also bet that if you went back to 1918, who was president then? Would have been just after World War I. Was it Wilson after World War I? But I don't think he was elected till 18, right? Was that an election year? Or was the election year 60? I don't know. Anyway, you probably find the word pandemic then too, but no other speeches, right? So it's a kind of a funny idea of identifying text. It's not only the writer, but also the thematic content of the speech that's going to help you identify. And that maybe makes me feel a little bit better about speech 2, which is the Gettysburg Address, because that speech is unlike any other speech that Lincoln gave or many of the other presidents gave, right? It's unusually eloquent. It talks about lofty, abstract ideas. It's not about production and wheat, the drought or the wheat production going down or whatever Hoover talked about. So it's not unusual that we would struggle with the Gettysburg Address. Okay, so we see where we're going. Everybody okay with this? Okay, in the template file, there are a couple of top-level, we lost some tabs here. Some top-level global variables. I don't really like the use of global variables in Python files, but in something like this, rather than, it's convenient for you to have a list of all the speech names and so on. So the variables are P, U, S, and regexp. So let's go over those one at a time. P is the list of the presidential names. And they're used to identify the speeches. They're not quite simple names, though, not just simple names. You'll notice that because we have more than one Roosevelt, Franklin is F.D. Roosevelt and Teddy is just Roosevelt. But more or less, it's just a list of last names, like G.W. Bush versus Bush. This is Bush 2, Bush 1. And then the list of unknowns. So this is our list of presidential names. Yes?
Since he was Cleveland was president twice.
I'm sorry?
I think it was Grover Cleveland.
It was Grover Cleveland was president twice, yeah.
I
I only have 4 speeches from Cleveland. I took them from the 2 periods. I didn't distinguish Cleveland 1 and Cleveland 2.
Okay.
Right, because it's the same. I figured it was the same president. Yeah, this is all a little bit arbitrary because there's hundreds of speeches from some presidents and very few from others that are at the Miller Center. Some of them are really long, and some of them are like brief remarks in a press conference. So I kind of picked at random. I'm not claiming that this is a representative sample in any stretch or form. I was just hoping to capture enough of the era that I might be able to hone in on, and my system would be able to identify the speech. If you really wanted to do this, you could go to the Miller Center's website and download literally probably 3,000 speeches. And that would be a more suitable corpus for something that is, you know, something more ambitious. Okay, the other thing you have here is you have a list of stop words. We'll see how we use these. Notice that these are all lowercase words. And finally, there is a list of regular expressions. These are actually tuples of expression and what you substitute it with. So these are the substitutions that get rid of contractions and possessives. They're ordered. So the first thing you do is you get rid of apostrophe S. Then you turn won't into will not, can't into cannot, and apostrophe T into space not, apostrophe RE into space R, and so on. So you apply each one of these in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 substitutions that basically contain all of the information that we did with 92 substitutions without the use of regular expressions. Okay? So this is the result of where we were going with our text processing and our foray into regular expression matching. Now, as it turns out, you won't actually have to use these because I do this for you. This is part of the code I provide. But I do want you to understand it. I do want you to make sure you understand how this works. All right, so we have these 3 or 4 special variables that we can use to refer to things conveniently in our code. And then we should look at one of these speeches too. So let's just for a moment open up the corpus here. Anybody got a favorite speech? Here, let's take that. Should we take the unknown that is, I think is number 2. No, that actually was identified correctly. I'm surprised. Wow, maybe I'm wrong. Maybe I didn't use the Gettysburg Address. Oh yeah, here it is. So what you get is in this case, a single line with the entire speech on it, including punctuation, commas, hyphenations, and so on. I did some cleaning up for you because these come from websites, so I stripped HTML. I removed as much of the markup as I could. But there are funny diacritical marks and things embedded in here. Certainly commas and parentheses and hyphens and so on and so forth. So you open up one of these things and you process it. That is our first step. As I create the instance of speech, the speech class, that's going to contain the Gettysburg Address, I have to read in that text file, which means I need to find it. So again, the system will look in the corpus directory. What actually does the work here is the __init___ method. In the speech class, there's very little code other than the init method. So we'll go down to the speech class and we'll take a look at this init method. The init method does a bunch of things. It relies on, in particular, a couple of instance variables. It sets up some instance variables with the speech. So you read in the text and you set up these 4 variables. The text variable contains the regularized text of the speech. By regularized, I mean it's still upper lowercase, but exclamation points, question marks, those have been replaced with periods. All of the punctuation has been stripped out of the text, so it's just sentences with periods. Then we have a version of this called sentences, which is the same as this one, but it's broken in, it's a list of strings that represent individual sentences. And finally, we have a list of words that are the words in text broken into words. Again, upper and lowercase are still respected. And finally, we have this WFREQ. So I apologize, my tabs are not coming out. But WFREQ is the word frequency dictionary, ignoring stop words. Now, we've done this before. On many assignments, we've built from text the number of occurrences of each word in the text. Here, the only difference is you ignore stop words and you turn everything into lowercase. This should be something that you're prepared to do. So I want to set up these 4 instance variables. Now, as it turns out, most of these variables actually don't get used in the code. And this is an artifact of stuff I removed to simplify. One of the things I removed was I wanted to get a readability index for each speech, which is why your Lab 11 is what it was, right? Your Lab 11 would have made use of the sentences and words and text of these 3 variables, right? Because you needed the whole text, you need to know how many spaces, how many words, how many sentences, you need to measure sentence lengths and so on. So you can imagine taking your Lab 11 and adding the forecast method to the speech object and get a readability index for every presidential speech. It's trivial to do. But I took it out because I didn't want to have too much in the assignment. So most of the work happens in the speech init, and it relies on a bunch of critical helper functions that are not methods, but are embedded inside the, that particular method. So let's take a look at those helper functions first. Oops. Yeah, I guess that's what I want. Yeah. So you can see here is the initialization method. It takes just a file name here, which you'll see shortly is composed of the directory where your speeches are, the president's name with a .text appended to it. And there are a couple of helper functions here. The first one is expand word, which takes a single word and applies a bunch of regular expression substitutions to expand contractions and flush possessives. Now, you know which substitutions to apply because I gave them to you in the top of the file. The regex list of tuples has the regular expression to search for and the substitution to make. So it's a single application of the resub command. You have to do these in sequence to that word until you get rid of all the apostrophes. The whole point of this word expansion thing is any apostrophes in the word are going to be taken out. Either they're going to be expanded as contractions, dropped as possessives, whatever it takes. Now, this is harder than it might seem, and you can't agonize over it too much because I want to point out that the apostrophe S we use in English for possessive is exactly the same device that we use for a contraction with the word is. So if I say Ben's wallet, that's a possessive S. But if I say Ben's tired, that's the Ben is tired contraction. And there's no way you can tell it apart from the text without some more sophisticated analysis of what Ben is. Is it a noun? Is it something that can possess? And what the likely context is and whether this should be an is or a possessive. So we're going to finesse that. It's going to be wrong about half the time, but we're going to get rid of that apostrophe S one way or the other. So that's one thing we're going to do. And then all the contraction apostrophes that are in there like isn't and so on, we're going to get rid of those. But those regular expressions should do that. This should be a fairly straightforward application. Expand text takes the whole of the text and basically uses expand word to regularize the text. And finally, there's this rather more ambitious function called flush marks, which is provided for you. And what this does is it removes any extra punctuation marks either in words or in the text, hyphens, commas, semicolons, anything like that. They just get removed. And they're removed, and the question mark and exclamation point, which are used to mark end of sentence, those are all replaced with the uniform period. So at the end of the day, when we look at this little indicative bit of code, which is on the slide, but it's maybe easier to see here, this is the core of the initialization thing. You need to understand this code, so let's look at it. We've seen this before. Open a file name was passed in for read as in file, And then there's that variable, self.text. We're going to set it to this expression. That's a pretty ugly expression. Let's see what it means. We'll start from the inside out. We know that infile read takes the infile handle, and what does it return? What does the read method of a file handle return? We've done this like a dozen times. Anybody? When you say read on a file, what do you get back? Yeah. You get a string that contains a line, a word, the entirety of the file. Actually, that's read line contains a line. Read gives you the whole file back. One fell swoop, it just says, open the file, represent the contents of the file as a string, and return it as your value. So this reads the whole Gettysburg Address in one string, complete with carriage returns and whatever else is there. And so you'll notice that what we do with this is we expand text first. And we know that expands text goal is to get rid of all the apostrophes and possessives and contractions in the word. So it does a first pass of the text file, expanding contractions and removing possessives. That value is the third argument to this RE sub. Now RE sub is a regular expression substitution. It says, substitute this pattern with this thing in this text. So we know that expand text of the read is the cleaned up Gettysburg Address. But here's a slightly different version of RE sub than we've seen before. So let's talk about that for a second. First of all, this regular expression has a grouping parentheses around it. It says take whatever it is that matches and call that group 1. And we see that this uses a lot of pipes. The pipes are alternate expressions. So this big regular expression here basically says 2 hyphens, 1 hyphen, a long hyphen, an underscore, a left parentheses escaped, a right parentheses, a comma, a colon, an apostrophe escaped, a double quote, an ellipsis, which is 3 dots, a question mark or an exclamation point. Any of these things match and return as a group. And one of the nice things about RE sub is that normally you give a string expression, a regular expression, and what you want to replace it with. And that what you want to replace it with is usually a string. That's how that regex tuple works. There's an expression and the string you replace it with. But you can also give a function name instead. And that function name will be invoked on the matching object. So here we're going to take any mesh like this, we're going to pass it to the function, this helper function, flush marks, with the argument being the match. And I'm going to check, if group 1 is one of these things, then I'm just going to return a space. So this says replace a double hyphen with just a space. If group 1 is one of these things, then I'm going to return the empty string. And this basically says get rid of any commas or parentheses. Just remove them. And finally, if group 1 is one of these things, question mark or exclamation point, change it into a period. So this is a massive regular expression replacement of punctuation and removal of punctuation. I didn't ask you to write this, but I do want you to understand this. So this RE sub does all these substitutions and returns a new string where I again do a regular expression substitution for one or more spaces are replaced with a single space. So wherever there are 2 or 3 spaces, they become 1 space. And at the end of the day, all of that's done, I'm going to invoke the strip method to remove any extraneous white space at the start or the end. So this is my cleaned up expression text. That goes into self.text. You don't have to do it. It's done for you with the exception of the 2 helper functions. These you're going to have to do yourself. Okay, so there's our, this is the passage we just looked at. Expand word applies the regular expressions that we saw before to regularize apostrophes. Expand text uses expand word to regularize the text. And flush mark removes all the extraneous punctuation and does a replacement of question mark exclamation point with period. So at the end of the day, let's see if I can bring up my. Where's my? What? This is not that. What happened to my? Sorry, I'm looking for. There's so many windows open. I can't find the Python shell here. There we go. By the way, I think I was wrong. Mystery speech 2 is not the Gettysburg Address. It's Nixon's resignation speech, and it caught it straight on. I was a little bit surprised. So, I'm going to build a speech object. Let's see, where is it looking for? Do I have that? Oh, let's do this. Here, let's do this. Nuts. All right, so that's, let's just get a, sorry. Let's just get a handle of one of these. If I look at this speech, I can find the text. Yeah, that doesn't help. There we go. So here is Obama's speech. You can see the text retains all of the upper lowercase, but for example, the commas and the 7 million jobs are gone, and you'll notice that there are no parentheses. It's just text separated by periods, and that's what we had hoped to get from this. So that looks good. And if I look at the, let's just look at the first sentence, you'll see that this is the very first sentence, the second sentence of the speech with the period removed, so we just get the sentences back. And if I ask for that, you see the first 100 words. Here, though, these are all lowercase, okay? All right, now, vector spaces. So to get our text to match these unknowns, we have to have a representation that we can match on. And the one we're going to use is something called a vector space. And the idea behind vector spaces is that word order doesn't matter. It's a word, you'll hear this called a bag of words representation. You take all the words in the speech, you throw them in a bag, and that's the representation. We've done what are essentially word vectors when we do word frequency counts. We have to do a little bit more work on those to be able to use them more in a more interesting way. So the idea here is that the pattern of the words you use, the relative frequencies of the word choices you make, can say something about who you are as a speaker. So these might be particular choices to a president. Tyler used to say great all the time. It's in all his speeches multiple times, like 20, 30 times. And Vietnam was only said by Nixon, Ford, Carter, or Reagan. But the way to think about a vector space representation is imagine a two-dimensional graph, right, where you have an x-axis and a y-axis. That's a two-dimensional vector space. But instead of labeling the axis x and labeling the axis y, let's use the axis x to represent how many times the word Vietnam appears in the speech, and the axis y to represent how many times the word great appears in a speech. And if you think about it, every speech then maps onto a location in this two-dimensional plane based on how many Vietnams and how many greats are in it. Some speeches will map to the same point, but all speeches will map to a particular point. Some may map to the origin because they use neither word, and that's okay. But that's the general idea behind a vector space. But what we're going to do here is instead of just two axes, instead of x and y, we're going to have a lot of axes. In the example I gave you, we used I think it was 1,500 words, so 1,500 dimensions. And each dimension corresponds to a word that was used in the speech. And the value, the magnitude of that direction in the vector, the value corresponding to that position in the vector, corresponds to a function of the number of times that term was used in the document. Okay, so the premise here is that two documents that have similar content, when you compute all of their word frequencies and their particular vector representation, they'll map onto a space that's near any similar document. You can sort of think about this. If I had documents that use great in Vietnam only from one speaker, they'll map to a particular space in the point in the space. The documents that use either Vietnam or great or neither, they'll map somewhere else. So based on the pattern of words, you can see that there can be some locality in the space. All right, so we want to come up with a set of word axes that are useful for distinguishing between the different speeches, right? So for example, it's probably unlikely that using stop words and stop word frequency will tell you much, because every stop word probably appears in every speech that's long enough. So our very first step is to remove the stop words when we compute the word frequencies. You've given a list of stop words to remove. Secondly, we need to make sure that document length doesn't affect the mapping. The Gettysburg Address is a very parsimonious speech, not a lot of words. So the frequency counts there will be by nature much lower than the frequency counts in Herbert Hoover's State of the Union address, which was very wordy. So we somehow need to normalize based on document length. The encoding we're going to use is something called term frequency inverse document frequency. And I would like to say that this is a very commonly used term in natural language processing. I would like to say that it means one thing unambiguously, but if you go to Wikipedia, you'll see there's variants of this measure, many variants of this measure. So stick to what's spelled out in the handout and you'll be okay. If you go to Wikipedia and choose the wrong metric, you won't agree with what the solution expects. So term frequency is just the number of times a word appears in a document. You saw that we had that W-freak speech measure, right? The W-freak slot in the speech class. There was going to be a dictionary of words and the number of times they occur. So you already know how to do that. You have to rewrite that code. So term frequency is the number of times the words appears in the document. We're going to normalize the regular word count by the length of the document itself. So in other words, we're going to take if we end up with great being in there 25 times, we're going to divide it by the length of the speech to get a normalized version. So we're going to divide by length to get it right. And the inverse document frequency is the number of documents in the corpus divided by the number of documents that contain this particular word. So in other words, it's a measure of how common this term is across documents rather than within documents. So think of this as the product of how frequent a word is within a document times the inverse of how frequent a word is across a corpus of documents. So this particular term here helps us find discriminatory words. So for example, Vietnam appearing only in 4 president speeches, that's a powerful word when you're trying to rule out the other 37 presidents, right? You know there won't be a Vietnam in it. So this term provides that kind of information. Whereas the fact that, I think it was Tyler says, I forget who it was, Tyler says great so much, that's characterized by this term. And we simply multiply these terms, two terms together, and we get a vector of these products. That's our representation of our document. So for each document, we're going to build this n-dimensional vector, right? So n is the number of words that we're using, where each weight is the term frequency, this is the normalized term frequency, times the logarithm of the number of documents in the corpus over 1 plus the number of documents that this particular term is in. So TI is the term we're trying to characterize the word. If it's in this document, given that it's in the document set. So we want to know 1 plus the sort of frequency of this term across documents. So TFI is the number of times the term appears in the document normalized by document length. This is the number of documents in the corpus, and this is the number of documents that contain the term TI. Now, there's some funny stuff here. There's a logarithm, there's an addition here, there's a 1 here. This 1 is not meaningful. This is where these formulas differ. The 1 here is just so we don't get a divide by zero error. It scales things so that you don't end up dividing by 0 ever. So it just avoids divide by 0, and the log doesn't matter what the base is, it's a scaling factor. There are all sorts of variants of this basic formula. The way to think about this is something about how many times the term appears in the document divided by something about how many times the term appears in, how many documents the term appears in. We say inverse document frequency because we do a product, and so we flip this around. Right? But that's the metric we're going to use. And now we're finally ready to talk about how we're going to do the identification. We're going to pick the top K words in the corpus. So we've already built the speeches, and we have our word frequencies for every speech. We're going to merge all the word frequencies to get word frequencies for the corpus. So every individual speech tells me you use the word America 7 times or 12 times. The corpus has a word frequency count which tells me you've used the word America 19 times, 7 in one, 12 in the other. So it does the frequency across documents. In the speech level, you do frequency within documents. And we're going to find the top K words in the whole corpus, not in the document, in the whole corpus, the top K words that don't appear in every document. The reason we want to exclude words that appear in every document is that if you look at this formula, if the word is in every document, then this term pretty much goes to 0. And the vector would have a 0 in it, right? Because if the term is in every document, it doesn't discriminate between documents, doesn't really add anything. So we're going to do a top K word pick, K is a parameter I give you, that don't appear in every document. So we want to make sure that they have some, they only appear in a subset of documents. And we can do this based on the word frequency counts in the speech class and the word frequency counts in the corpus class. So I'm almost done here for today. We'll talk more about this next time, but let's just quickly look at the corpus class. So the corpus class has the directory. There's the directory where the presidential speeches are found. It has a dictionary of speech objects that we construct. So Obama 1 is a speech object. We can get to the instance of speech. We have word frequency distribution across the corpus, which we're going to compute from the individual word frequency distributions. We have a document frequency distribution, which tells me how many, for each word, how many documents it appears in. And finally, we have a template, which we're going to use when we identify which words constitute the axis of our match. So when we do that top K word, we set up the template that tells us for each document, these are the words we use. Yes?
What do you mean by the parentheses in the comments of
Oh, okay, so the word frequency distribution does not include stop words, right? So in our speech objects, we have text, which includes the whole text, sentences and words, which include everything. But when you compute the word frequency, you're to avoid computing word frequencies for stop words. Stop words are factored out. Well, we're sort of out of time, but that's the brief run through this. My advice to you is read the document that came with it and start working first on on being able to read in a speech, right? Just create an object of type speech and manipulate it in the REPL to read in one of those speeches and make sure that you set up text, sentences, and words. That's the first step. And then we'll take it from there on Friday. I'll tell you where to go next. All right, good luck.